Thanks everyone for attending. So as you're expecting, today we're going to be talking about foundation models and how we're building these and using these to solve problems across Nubank. So before we get into the details and application and everything, I want to give a brief overview to sort of prepare you for what we're going to talk about today. So to start, we're going to cover, why we want to use foundation models. We're going to go over a bit of a motivation to understand why we want to do this. And as part of this, we're going to start to uncover some of the problems and things we're going to need to build to actually apply our foundation models to transaction data. So building from this, we're going to show how we construct our sort of base foundation model and how we use self-supervised learning to pre-train this on our transaction data. The next step is to explore how we can use supervised fine-tuning or supervised joint fusion to train these models for specific tasks that we might have labels for that we want to solve. So how do we take our pre-trained model and produce some embeddings that are specific to the task we want to solve? Then almost at the end, we're going to talk about an application. So we're going to show how we apply this to a particular problem that we want to solve and show how this performs over, say, a more simplistic baseline. And then to finish, not shown here, but to finish, I want to talk about how we are currently researching new ways to extend these foundation models. So what the next generation of these models are going to look like and why we want to move to this next generation. Amazing. And before I get started, I also want to make it clear, I'm sure as everyone knows, while I'm the one that is lucky enough to present this work, all this work is a result of many wonderful, fantastic engineers at Nubank. So I just want to make sure credit is given where credit is due. And you can see a lot of the names and stuff if you've read the blog posts. A lot of the people who worked on this are listed in there. Amazing. So to get started, I want to talk to you guys about why foundation models are something that we want to do. So to understand this, we want to go back to the basics. So it's an industry standard to use things like tabular feature models to solve a lot of the problems we might have. So for example, using gradient boosted trees like XGBoost or like GBM trained on handcrafted features. And as the name suggests, these handcrafted tabular features are typically manually constructed by data scientists or domain experts. So to give an example, say I want to predict, is a user going to churn from Nubank? Now, as a domain expert, I know that things like your average debit spend or average credit spend are important factors in determining this. So I take the transaction data that I have access to, and I construct these features, and then I use these to train my light GBM model. Now, the advantage of this is that this is a simple approach, and it's also relatively interpretable. I can look at the model and I can look at the features, and I have some intuition as to what's going on here. But the challenge here is that this actually requires a little trial and error. So I go through this process for this churn example, and then I train my model and I evaluate it, and I find, oh, actually, maybe this doesn't perform as well as I thought it was going to. So I have to go back to the drawing board and figure out what features am I going to add or change or remove to improve this model. So they rely on a lot of trial and error in this situation. But over time, we can get to a model that works pretty well. The other thing is that while these features are interpretable, there's no guarantee that they're going to be optimal. So while they're interpretable and we can understand what they're doing, there might be better features that we can design that are maybe less interpretable or harder for us to understand. So also harder for us to design as humans. And these types of approaches also typically ignore things like string features, which can be quite hard to capture with tabular features. And these sorts of string information, like the description of a transaction, can be very useful for understanding a user's behavior. So it's important that we find a way to incorporate this into the model. Now, the other thing is that the solution is not entirely scalable. So what do I mean when I say scalable in this situation? So what I'm talking about is that in reality, we don't have just one problem that we want to solve. Rather, we have maybe 100 or even 1,000 problems across all of Nubank that we want to solve. And so in each of these situations, what we end up doing is we have a domain expert or these data scientists constructing these handcrafted features for each of these problems. Now, in some situations, we can share these features across tasks, but maybe in a lot of cases, we can't do that. So there's a lot of repeated work going on here where each team is coming up with their own sort of collection of handcrafted features. So while we're trying to move towards this idea of foundation models, we want to first look at this idea of automatically learning features from the domain. So it's pretty common in other fields like image processing or audio to learn features directly from the input domain. So what I'm saying here is there's this figure on the right-hand side shows an example of this. So on the left-hand side, we have the input domain, and then we have this handcrafted feature engineering part where the data scientist or the domain expert is manually designing these features, and then these are fed to a classifier to produce the final prediction. However, what's often done in things in domains like images is you'll have some sort of feature extractor network, which is trained end to end as part of the classifier, which extracts these features automatically and learns these more expressive features that maybe are harder to construct. So, for example, for images, this might be rather than using, say, like an edge detection filter, which we then use to then manually construct some edge features. We just allow our model to use CNNs to learn these features directly from the domain. And so what we would like to do is we would like to do something similar for transaction data. We want to have some way of, rather than relying on manually constructed features, we want to learn them automatically from the transactions. This removes the trial and error. Now each team can learn the features that are optimal for their particular task. But of course, to solve this, we're going to need some way to interface between these sort of the sequence of transactions and the neural network models that we want to train. But of course, the question is this approach scalable? So we've solved some of the problems we had before, but supervised learning is typically quite data hungry, so it can require a lot of labels. So this is one way this approach is not scalable. So this is where we arrive at this idea of foundation models, which have become quite a significant trend in machine learning. And the general idea here is this sort of learn features once, or in a sense once, and then to use them everywhere. So we have then a sort of a two-step process where the first step is we use self-supervised learning to produce general embeddings without relying on task-specific labels. So this involves generating labels from the data in a self-supervised way. So for language, this is often doing something like training the model to predict the next word in a sentence, or we might mask out words in the input and predict the words that we've masked out. So next token prediction or masked language modeling. The second step is we take these pre-trained models and we want to use them to solve a downstream task. This is the use it everywhere kind of aspect of the model. And so this is where the fine tuning comes in. So we have these general embeddings, which perform pretty well. And then we want to take our set of labels that we have and tailor these embeddings to be good for a specific task of interest that we want to solve. This is what each team would be doing to take this general model and then apply it to their particular domain problem. So the advantage here is that rather than requiring a huge amount of labels to train our model, we can do this pre-training step, which can take advantage of a large amount of unsupervised data or data without explicit task labels. And then we can use, say, a smaller set of labels to train these for a particular task. The figures on the right-hand side show some examples, and the figure down the bottom shows sort of the vision for what we want to do at Nubank. So in this talk, we're going to talk a lot about transaction data and how we're modeling transaction data. But the vision here is that we can encapsulate much more, right? So transactions capture perhaps one relationship between Nubank and a customer and a member, but there's other things that we can capture too, like customer support interactions or app events, how users interact with the apps. So in the long run, the idea is to sort of use these foundation models to capture not just one aspect, transactions, but all of this. And then you can see we apply this then across all these different tasks like product recommendation, income detection, fraud, these kind of things. Now, the last thing we want to understand before we start building our transaction intelligence models or user intelligence models is this worth it? There's a lot of hype surrounding foundation models. So we want to understand from the literature, like, is this something that can benefit our particular use case? So we've proposed a very lofty goal, which is be able to understand user behavior from these foundation models trained on transaction data and want to apply this across all our tasks. So I think if we look at the literature, there's a lot of places that use these models to solve problems that involve learning from sequences of events. So for example, there's LinkedIn, there's Pinterest, there's Meta. In each of these cases, the company is trying to learn from a sequence of user interactions with particular objects. So for Nubank, this is transactions. But for LinkedIn, this is interaction with ads. For Pinterest, this is interaction with pins, so they can learn which other pins to recommend to a user. For Meta, this is like interaction with posts on Facebook to learn which post should we recommend. In all these cases, we have a sequence of events, and these events can consist of multimodal data. So we might have images in some cases, text, and other tabular data. And this very closely models our situation that we want to solve. In all these cases, across LinkedIn, Pinterest, Meta, and other situations as well, these models typically produce very large improvements over just using tabular features only. And often these models have been deployed to production. So this is very promising, a very promising indicator for our applications. Amazing. So now that we understand why we want to build foundation models and we have some intuition as to why we think these are going to work for our particular case, we need to actually build them. And so as part of the motivation, we understood that we want to sort of get this idea of automatic feature learning working from the transaction data. But to do this, we need to build some sort of interface between the transactions and our foundation models, in this case, transformers. This is what we're going to cover in this section. So the general idea here is we're going to build on top of standard generative language modeling tasks. So in other words, we're hypothesizing that by predicting future information about a user, in a sense, predicting future transactions, the model will learn to efficiently summarize the user. This is what's done with text. And so this figure here shows the general structure of the model that we're proposing. We have a sequential model, which takes our transactions as input. Of course, we need to define this interface. And then we're predicting the future behavior, which in this case is the future transactions. So we chose transformers for two main reasons. So one, they afford training and inference efficiencies compared to, say, like RNN models. This is due to their ability to facilitate parallel computations when we have all the inputs. And since we're computing embeddings at the output, we're not doing autoregressive generation. We don't have this issue of, we don't have this issue at the output where we have to worry about like key query, key value caching and stuff like that. We can just compute our embeddings in one pass. Secondly, they tend to be better at capturing long-range dependencies in the input. And this can be very important for things like transaction data because there are often seasonal spending patterns. For example, people spend more in the holiday periods. And so being able to capture these sorts of long-range signals is very important. So again, before we can use transformers, we're going to need to formulate an interface between the transactions and the transformers. So to be more specific, transformers or attention-based models are sequence-to-sequence models. They're a sequence-to-sequence operation. They operate on a sequence of embeddings. They take a sequence of embeddings as input, and they produce a sequence of embeddings as output. However, in our case, we've got a sequence of transactions, which are in essence, a sequence of dictionaries, right? So we have a sequence of dictionaries, which are key value pairs, like the description and then a text string. We have the date and a date string. We have the amount and then a floating point value for the amount. And what we need is some method, some way to formulate our transaction data that allows us to convert it into a sequence of embeddings that our transformer can process. So if you read the blog post, we discussed a few different approaches. In this talk, to keep things concise, we're going to just sort of discuss this idea of text is all you need, which then directly motivates the solution that we propose. So we have this idea of text is all you need, which is what we base our approach on. And the idea in this situation is to essentially convert our problem of modeling users into a problem of modeling text, modeling strings. So we will come up with some way to construct a string from each transaction. And then we can construct user strings by simply joining these transaction strings together. And now we have this text modeling problem where we can just use standard natural language techniques to solve it. So for example, once we have these user strings, we apply a standard tokenization process as we would with any other natural language problem, which gives us a sequence of tokens. We can then produce our sequence of embeddings using an embedding lookup table as we would with other natural language problems. So now we've got this process of converting our sequence of transactions into a sequence of embeddings, which our model can deal with. In this case, in the text is all you need case, the way that this conversion happens is, you can sort of think about it as just kind of JSONifying the transactions. So we just flatten our key value pairs into one long string, and then we apply this tokenizer. Now, the one issue here is that now each transaction corresponds to potentially like many, many tokens. And this rapidly fills the context length of our model. So this is an important thing we need to understand. Why is this a problem, or why do we need to be concerned about filling the context length of our model? So when we talk about the context length, what we're saying is this is the sequence length, the number of tokens or the number of embeddings that we're providing as input to our model. As we increase the length of the sequence, the cost of using attention scales quadratically in terms of the memory and the compute required to do this operation. Now, attention is like the main building block or the main thing that's doing computation in transformers. So often there'll be many, many repeated applications of this. So if we increase the cost of this, this can mean the models can be very expensive to run. So we need to be very careful with this. Now, in the case of Tech is all you need, each transaction can take up roughly 25 to 30 tokens. So for a context length of, say, 2048 tokens, this is only roughly 70 transactions per user. So for some users who have very frequent, who do a lot of transacting, do a lot of purchasing, 70 transactions might not even cover a week's worth of their behavior. So this is an important consideration, because for making some decisions or predicting certain behavior about the user, we're going to need a long time horizon. So of course, there's many techniques we can use to make attention less costly. There's flash attention or other more efficient kernels that we can use. Or there's things like sparse attention or like approximate attention. So like the sparse attention could be like Big Bird or, the linear attention kind of setup. But the one lever that I think, before we sort of fall back to these approaches, the one lever we can really work with is making our representation of the transactions more efficient. So reducing the number of tokens that we're using per transaction. So this is what leads to our tokenization approach. And the idea here is that we rely on what we call like special tokens, or what are called special tokens. So rather than JSONifying our transaction dictionary and then tokenizing it as such, we essentially process the transaction to a collection of special tokens plus whatever the natural language description is. So this figure on the right-hand side shows the structure. So in this case, we're dealing with a transaction that has the amount, the date, and the description. For the amount, this corresponds to two particular special tokens. So first we have the amount sign. This tells us whether it was an inflow or outflow transaction, whether it was paid or received. Then we have the amount bucket. Now this is like a quantized version of the amount. So one thing that transformer-based models often struggle to deal with is numerical features, like how to process these. So to overcome this, at least in this situation, we apply sort of a quantization. So we have a collection of buckets, and then we say each amount falls within these buckets. I think there's like 21 or 22 different buckets that we have at varying resolutions depending on what the value is. So more resolution in the lower values, less resolution as you get higher, above 100 or 1,000. So in this case, we have an amount that's between 20 and 30. We then have three features or three special tokens that correspond to the date. We have the month, so month February. We have the day, so which day it is out of 1 to 31. And then we have the weekday, whether it's a Monday, Tuesday, Wednesday. And now finally, we have the description. So when we apply our standard natural language tokenizer, we've set this up in a way which knows how to handle these special tokens. So now rather than having, say, an arbitrary number of tokens, depending on what length the amount is or stuff like that, we now have exactly two tokens for the amount, one for the amount sign, one for the amount bucket. We have two tokens, so three for the date, and then we have an arbitrary number for the description. Of course, in this case, we still have this problem where a transaction corresponds to potentially many tokens, but in this case, we've reduced the scale significantly. So now we have roughly 14 tokens per transaction as opposed to 30. This allows us to fit a lot more context in our transformers input. Okay, so now that we've constructed this interface based on special tokens, we can put this all together to end up with our token level foundation model, what we call the token level foundation model. So just to cover this like end to end, what we have here is we start with a sequence of these transaction dictionaries, a sequence of these transactions, and we're going to convert this into a sequence of embeddings, which our model can process. So we start by converting each transaction into a string using the aforementioned process, that involves special tokens. And then we join these strings together to construct the user string. So now we have a user string which describes the user's transaction history. We then apply a tokenizer, which handles these special tokens accordingly and tokenizes natural text, like the description, for example, as you would any other natural text. And then we convert these tokens to embeddings by using a standard learned embedding table. And this forms the input to the transformer. Now, our transformer operates on this input sequence and produces a sequence of output embeddings. And we can train this model using standard natural language techniques like next token prediction or masked language modeling. So, of course, up until this point, we've kind of talked about this transformer as just a transformer, some sort of model that we use. But in practice, there's, of course, many different kind of configurations we can use here. So this was something that we explored in detail. So the idea here was we had a collection of benchmark tasks, and we wanted to explore how good, for different model configurations, our pre-trained embeddings were. So in this case, there's no fine-tuning. We just have our model, which we train with our self-supervised loss. And then we take the user embedding produced by this model. In this case, the user embedding is just the final output embedding. So just to go back to the slide, if you look at the right-hand side of the figure, we have this sequence of output embeddings. This final red one would be, for example, the embedding that we take to be representing this user. Of course, there's different approaches you could use to aggregate this. You could say have like a mean pooling, or you could take the first one. We just found in practice this worked the best when we were doing our experiments. So we take this embedding, which represents the behavior of that user, and then we train a simple logistic regression model. In this case, the benchmark task that we're comparing on binary classification tasks. So we train a logistic regression model to predict each of the labels from the embedding. And then we report the average performance across these tasks, or specifically, we report the improvement in the average AUC as we change our model configuration. So for reference, like a relative improvement of say 1 to 1.25 points on these tasks is usually pretty significant. So the models we tested, starting with the baseline, was simply, so model 1, which is not shown in the graph because we're showing the relative improvement over that model, is simply a bidirectional attention model, so a BERT style model trained with the masked language modeling task. So then chunked model 1 is an initial attempt at trying to extend the context length of these models, but this is purely done at inference time. So chunking involves, so we generate one long string, say of 8 times the context length, but then we process each chunk individually. So we process the first 1,024 tokens, then the second set of 1,024 tokens, and we average the result. And we can see that we can already get a reasonable improvement simply by considering the additional context of a user, but in this rather primitive way. Now, model 2 extends this by using a sparse attention model. So I think we used Big Bird in this case. And this allowed us to extend the context length during training to 2 times the initial context length, so to 2048 from 1024. Now, we can see in this case, we get an improvement over using all this context to inference time. We get an improvement just by training with this additional context. So not only is having this additional information important, but it is important to also train our model with this additional context, and it can take better advantage of this extra information. Now, chunk model 2 is very similar. We're just applying fewer blocks because we have a longer context length in our model. So now we're doing 4 chunks and we average the result. And again, we get a nice improvement in performance. Now, model 3 is where we start to really change the structure of the model. So we switch to a causal attention setup. So rather than a BERT style model, this is more similar to a GPT style model now. And we add no positional embedding. And we also use flash attention. And so these changes all combined allow us to actually train with a context length of up to 8,192. So originally what we were achieving with our chunking, we can now train with that context length. And we don't have to rely on this sort of primitive chunking procedure. And we can see we get a very substantial improvement. And now we can move to model 3 large, which increases the parameter count by a factor of 4. And again, we get a nice improvement from this too. So the final thing you can see on this graph is fine-tuned large models. So essentially, we've got to the point where we have a model we can pre-train and we can evaluate how good these embeddings are across a range of downstream tasks. But in lots of these situations, we might want to learn embeddings that are tailored for these specific tasks. So we want to take advantage of these labels that we have and optimize the embeddings to learn features for the specific task at hand. And so this is where we get this idea of supervised joint fusion or supervised fine-tuning, depending on what procedure you're using. So, as I said, in the previous section, we outlined an approach for pre-training our transformers on sequences of user transaction data. And this was based on the idea of formulating our user modeling problem as a text modeling problem. And this was all done in the context of pre-training using self-supervised learning tasks. But in practice, we often have this labeled data, and we would like to take advantage of this labeled data for learning task-specific features. And this process is known as fine-tuning. So now, if this is all we want to do, then we can use something like this naive supervised fine-tuning setup that we describe here. So what we would do is we would simply augment the pre-trained model with an additional MLP network. This is called the classification head. And we would use this classification head or this classification MLP to predict our label. And we would train this classification MLP to predict the label from the user embedding. Except we also, in this case, allow the transformer to be trained as well. So now we're training the classification head, but we're allowing the gradients from the classification head to propagate backwards to the transformer, so the transformer can learn task-specific features from the transactions which we provided as which we're providing as input to the model. We often find using something like a parameter efficient fine-tuning method is very important here. So something like LoRa, for example, if you're familiar with that. So this is great, but in practice, we need to go one step further for a lot of the problems that we face at Nubank. Importantly, naive fine-tuning is not sufficient for us to achieve state-of-the-art performance on all of these tasks, a lot of the critical tasks that we're dealing with. And you might ask, why? So the thing is, we still need to consider tabular features. And obviously our lofty goal at the beginning of this talk was to completely eliminate the need for tabular features or any of this manual feature engineering. But there's sort of two situations where we actually still need to rely on these tabular features. So firstly, as I said at the beginning, our goal is to expand these foundation models across all data sources that we might have access to at Nubank. However, at the moment, we are simply restricted to transaction data. So for any source that isn't transaction data, we still need to compute these handcrafted features or rely on these handcrafted features. The other thing is that there might be data which is just simply tabular in nature, but still very important. So for example, bureau scores or bureau data, which you can buy from the central bank and has information about previous loan history and stuff like this. This is given to us in a tabular form. So we still need to be able to model this data because it's an incredibly powerful signal. So we need some way to incorporate this into our fine-tuning process. And we need to do this to be able to achieve state-of-the-art performance on a lot of these tasks. So the simplest way to blend our user embeddings with the tabular features is this approach known as late fusion. So the idea or the essence of this approach is to use the fine-tuned embeddings obtained through some sort of naive fine-tuning approach. And then we combine this essentially as a feature inside the baseline model, the light GBM or XGBoost model that's trained on our tabular features. So this figure on the right-hand side shows the two-step joint fusion, late fusion process. So again, first we have this naive supervised fine-tuning process, which allows us to learn embeddings that have task-specific features. Second, we have a model which takes these embeddings from the transformer, but the transformer is now frozen, and it combines these embeddings with the tabular features to produce a final prediction. Now, in practice, this performs pretty well. But the main issue that we have here is that the embeddings aren't optimized with knowledge of the tabular features. Now, this might seem kind of niche, and you might ask, why does this matter? But the thing that we hypothesize that is important is that there might be some features in the transaction data which only become useful if we have access to the tabular features. So if there's any sort of interaction that's important to capture between the tabular data and the transaction data, the late fusion approach misses this and doesn't account for that in the optimization. So to address this, we would like to do some sort of like joint, we'd like to have some sort of joint process. We'd like to jointly optimize or jointly do fine tuning with the blending procedure. And such an approach would be denoted joint fusion. So this figure on the right-hand side shows the general structure of joint fusion, which looks very similar to late fusion, except now you can see that this entire process happens as a single step. And again, this is preferable for two reasons. So firstly, which I haven't mentioned yet, since it's a one-step process, it's less prone to data issues. So when we do late fusion, we have to be careful about, not to do the fine-tuning step. We have to make sure the data we use for the fine-tuning step is disjoint from the data we use for the blending step, because you can have label leakage if you don't do that, and that can result in overfitting. The second issue, the second advantage is what I already said, which is that we can learn signals from the transaction data, which maybe aren't useful unless you have access to the tabular features. Now, the issue here is that while this seems like a logical thing to do, currently a lot of the blending module, or the model we use to do the blending between the embeddings and the features, is a gradient boosted tree model, which does not facilitate propagating the gradients back from the blending module to the transformer. So we can't do joint fusion and do blending with a gradient boosted tree. So the solution here is to use deep neural networks to do blending. However, if any of you have tried to use deep neural networks for tabular features, you know it's not quite that simple. So I think there's a great paper that I've read a while ago called "When Do Neural Nets Outperform Boosted Trees on Tabular Data?" And in this paper, they compare 19 different models. These are both neural network based models and gradient boosted trees, and they compare them across 178 benchmark data sets. And I think the most interesting finding is that for every model, there exists a data set, or almost every model, there exists a data set where it performs the best, but there's also another data set where it performs the worst. And this also applies to the gradient boosted tree models. So it's not just specific to the neural network models. However, on average across all these tasks, the gradient boosted tree models perform the best. So what this suggests is that there's not going to be a one size fits all approach that works for every problem. We're going to need to study what DNN setup will work well for our tasks. This doesn't mean it's impossible to use DNNs to solve these problems, but it just means we might need to find task-specific configurations, which might at some point involve a search over these different blending networks. Okay, so the refined joint fusion process that we ended up with that worked pretty well involved 4 key improvements, 4 key steps or 4 key improvements. And what I'm going to do here is just tell you what these improvements were. And then in the next section, we're going to look at an application. And in that application section, I'll show you how adding these changes in affects the performance of our blending module, eventually leading to it performing better than gradient boosted trees. So the 4 key things: firstly, adding categorical and numerical embeddings. Now, categorical feature embeddings are relatively straightforward. For this, you just have your learned embedding table, and for each possible realization of each categorical feature, you can go to this table and you can obtain the corresponding embedding. On the other hand, numerical embeddings are a little bit more complicated, but there's this paper, put the link down there, on embeddings for numerical features and tabular deep learning. They have 2 different approaches for constructing embeddings of numerical features. We use this periodic embedding strategy. So essentially, you project your one-dimensional tabular feature onto a vector of frequencies, and you apply periodic activations like sine and cosine. And this works really well. So then you have this deep and cross network V2. So using the DCN V2 as our blending module was also very important. And then in terms of actually when we do the joint fusion, embedding normalization is very useful. Without normalizing the embeddings, this can cause a lot of variance in the model performance, and in some cases overfitting. And then also regularization. So as with lots of things in machine learning, adding regularization was very important for achieving parity between our DNN models and the gradient boosted tree models. Awesome. So we've gone through this process now of motivating why we want foundation models, then exploring how we can build an interface between transaction data and our transformers, which allows us to utilize self-supervised losses from natural language like next token prediction or masked language modeling. We then looked at how we can use fine-tuning to tailor these models for specific downstream tasks, and how that for a lot of the applications we have at Nubank, we still need to incorporate tabular data, and this led to our joint fusion approach, which we just described. So now we're going to look at actually an application, like a real-world application, which this model is currently being deployed. So the application that we look at is a RecSys application, a recommendation system application, and it's a binary task. So we have a 1 label represents a positive user interaction with this particular product, and a 0 represents no interaction. And the label is time delayed. So we're attempting to predict the user behavior in 6 months from the label date. So this figure at the top on the right-hand side gives a demonstration of what we're looking at here. So We have the user's transaction behavior. There's T1, T2 up to T5. Of course, in practice, there's often many more than 5 transactions. And then we have the label date, which is where we're trying to, the date at which we're trying to make this prediction. And what we're interested in is 6 months from the label date. Is this user going to have a positive or no interaction with the product? We have 203 million training rows to use. In this case, a training row doesn't necessarily mean a unique, it's not necessarily a unique user. It's a unique user label combination. So we might have multiple settings of the same user, but they occur at different times with different transaction sets and potentially different labels. And importantly, the periods or the time periods covered by the train, validation, test set, these are all disjoint. So we're training it and evaluating it in a way where we want to be sure that the performance is going to hold as we get further from the train set in time. The baseline is a light GBM model trained on handcrafted tabular features only. Again, you can see the structure of this. We have both the transaction data and the other data. We have the handcrafted features from both these sets. These are combined, and then the light GBM model makes the final prediction. And our goal is to achieve a relative or absolute improvement AUC of 0.5 in the test AUC. This is normally significant enough to warrant launching a new model. So as I promised, the first thing we look at is how can we achieve feature modeling parity with the DNN? So with respect to the joint fusion process, we have to rely on these DNN models to do the blending, but there's no point in using joint fusion if we aren't convinced that the DNNs can model the tabular features as well as the gradient boosted trees could. A lot of these tabular features are very powerful, so it's important that we can model them correctly. So we first need to validate whether our DNN approach, the one we presented a few slides ago, can achieve parity with the gradient boosted trees. So this graph, this bar chart on the right-hand side shows how the performance changes as we add or change the configuration of our blending network. So on the left-handmost model is a simple multi-layer perceptron model. And we see that this almost achieves our desired gain in performance, but in the wrong direction. And then we individually explore the DCN-V2 and then the MLP plus numerical embeddings. We see in both these cases, while the performance is still below the baseline, we get quite a substantial improvement over our original just basic MLP setup. And then on the right-hand side, after the baseline, we combine these features, so the DCN-V2 plus the numerical embeddings. This is able to beat the baseline. This is very promising. And then again, by adding this regularization, we can get a further gain in performance. So we're able to achieve roughly a plus 0.08 AUC improvement purely by just improving how we model the tabular features through the DNN approach. So the next step, now that we've established that our DNN blending approach is good and we should use it, now we can start to explore joint fusion. So what we want to do is we want here to first explore how our joint fusion is going to scale across multiple different dimensions. This is a relatively primitive scaling exploration if you've read some papers that look at scaling foundation models, but we hope in future work to make this exploration in much more depth. But for now, we explore these 3 different dimensions. We explore the model size. So we explore 2 different model sizes, 24 million parameters and 330 million parameters. We explore some different context lengths, so 2048, 1024, and 512. And then we also explore various dataset sizes for joint fusion. And so for this, our baseline setup is a context length of 2048. We use 20 million pre-training rows and 20 million joint fusion rows. And then we have these 2 model sizes. We have the 24 million and the 330 million. And overall, we see some very promising scaling properties here. So firstly, larger models perform better. This is a good first step. We also see that more joint fusion data is better, also very promising. And finally, we see that the longer context lengths are better. But on this last point, I want to emphasize that we see the larger models can make better use of the longer context length. So not only does having the longer context length benefit our model in terms of being able to understand a longer time horizon of the user, but the larger models are able to better access this data or better learn the insights from this data. So this is very promising for scaling these models further in the future. So now that we have our DNN parity and we understand how to scale joint fusion successfully, we can put everything together to produce these final results. So by taking advantage of the larger model sizes, the longer context length, and all the training data, in the previous figure, we explored up to 100 million rows, but given the success of that, for this final one, we just train on all the data we have. And we compare, well, what we're interested in doing is comparing three models. Well, we have four models, I suppose. We have late fusion with the light GBM and late fusion with the DCNV2. We have the baseline model, which is the light GBM model trained on only tabular features using all the data. And then we have the joint fusion model. So firstly, we see that the late fusion approaches can get roughly 2x the usual improvement that we would look for before deploying a model. But again, we see this joint fusion approach is able to get roughly 2.5x this improvement. And this sort of validates our hypothesis that doing the fine tuning with access or with knowledge of the tabular features is very important for getting the sort of maximum performance that we can achieve. And the one point I want to really emphasize here is that we're able to achieve these lifts without adding any new data sources. So rather, the only change here is the representational capability of our model. We're learning better representations of the transaction data, and this is how we're achieving these lifts in performance. This isn't by adding new data sources, which I think is an important point. So one of the potential challenges with these models was their ability to be stable, to maintain this improvement over time. So for example, as I showed in the previous slide, we get this massive advantage from improving our representational power, or the ability to learn powerful representations from this underlying data. Now, of course, this gives us better performance, but this also might mean we might overfit to specific time periods. So, maybe there's some sort of particular distribution of the transaction descriptions in the training period, and the model fits to this, but this changes as we get further from the train period. Maybe some merchants change how they encode their transaction descriptions. And then the model cannot handle this, for example. This also might happen because of this, in this case, we have this label lag. We can't train on the freshest transactions. So what we want to do is make sure that as we get further from the training data, the performance gain over the baseline stays the same. So what we did is we constructed a 6-month, an extended test set, which spans the 6th month after the training and validation period. And we plot the relative improvement of our challenger model, of this foundation model, over the baseline for each week as we progress further from this training validation period. What we see is, while it's relatively noisy, we also see that this improvement is stable over time. So we don't see a decreasing trend. So we can be more assured that this improvement that we have will be maintained as we get further from the training period. So one thing I've completely left out of this talk, I've just sort of talked about this idea of we have transaction data that we're training on, and we have these transaction attributes that we're using. But of course, a lot of thought and effort actually goes into choosing this. And because of the restricted context length of our models, we want to make sure that all the information we give our models is, earning its place in the input, because we suffer quite a substantial efficiency cost by adding unnecessary information. So this is a very challenging topic, and luckily, Taylor, one of the other MLEs in the AI core team, has written a blog post about this, about how we go about choosing data sources, experimenting with data sources. And so this is going to be in a forthcoming blog post. So I would keep an eye out on LinkedIn or on the Nubank blog if you're interested in learning more about this. Okay, so that's sort of the end of the presentation in terms of introducing the initial version of our foundation models. But I wanted to give you a quick sort of feel for the kind of research we're doing now to produce the next generation of these models. So by further improving the representational capabilities of our foundation models before we finish. So to understand what the next generation is going to look like, or why we want to produce the next version of these models, we need to understand the pros and cons of the token model. So the pros, firstly, it's a straightforward objective. So we've formulated this representation as text, and we can use standard tasks like next token prediction or masked language modeling, which are nice, simple classification objectives. And also it works surprisingly well. So you might have thought at the beginning, this seems like a simplistic representation of transactions, just simply using text, but it works very well, as you saw in the application section. Now, the cons. So of course we have this context length issue where we rapidly fill up the context length with 14 tokens per transaction. We also saw, the other thing is that there's kind of an arbitrary ordering here. So we use a causal model. which means that this ordering that we sort of impose on the information, we say it's the amount, the date, then the description. This actually matters, and the model spends a lot of effort, learning the grammar of these user strings, despite the fact that this is something that we hallucinated up in a sense to make it work, to make our formulation work. The final thing is that we have this predicting subwords problem. So when we first sort of discussed our lofty goal at the beginning, we talked about we want to predict future transactions, and this is going to help us learn to understand user behavior. But now we're sort of in the situation where we're predicting subwords, we're predicting these tokens and not quite at the transaction level. So what would we like to do? What would we ideally do? The general idea is that we can represent each transaction as a single embedding in our sequence. So this removes this problem where we have like multiple tokens per transaction. So if we consider the attention efficiency with respect to the number of transactions, the token level model has an efficiency in order notation of 14n squared, but this transaction level approach would have an efficiency of n squared, so significant savings in terms of memory and compute cost. But of course, while this is a nice idea, there's two important questions. How do we construct such a model? So how do we vectorize the transactions? We need some way of converting our dictionaries into transactions. And the original way we got around this was using this text-based formulation of the token level model. But also, how do we construct our objective? If we're moving away from next token prediction, what does it mean to predict the next transaction? And so the approach that we've kind of settled on that seems to work quite well is the idea of learning these transaction embeddings end to end. So the idea here is that we're going to have some sort of transaction encoder, which accepts arbitrary numerical, categorical, or text features from the transaction and encodes these into an embedding. This actually, if you remember when we were talking about the joint fusion process and how we construct these blending networks, the structure of this encoder is very similar to the structure of a blending network. And now we have a transformer that simply operates on a sequence of these transaction embeddings. And in terms of setting up the next transaction prediction task, in this case, we can set it up as predicting the attributes of the next transaction. So we use a regression loss to predict the numerical features. We use a classification loss to predict the categorical features. And actually, we use a next token prediction loss to predict the string features of the next transaction. And the nice thing about this is once we've set this model up, which we have done, it actually is completely compatible with our joint fusion setup. So we can iterate on this foundation model formulation, and immediately deploy it and use it with our joint fusion setup as well. And so to give you an idea about the performance improvement, this is an example of using naive fine-tuning. So we're not fine-tuning with features here yet. And so the improvement is probably larger than you would see than if you used features as well. But we use this to solve the previous Rexus application. And so here we can achieve roughly a 0.5 AUC improvement. And again, this is simply by improving how well our models can represent the transaction information. Again, not by adding new transaction information into the sequence. Okay, so this is the end. Just to briefly recap what we've covered, because we've covered a lot. So we started by talking about why we want to use foundation models, and we want to use them to automatically learn representations directly from the data without having to rely on manual feature engineering. We then saw how we can build our first iteration of the transaction-based foundation models by relying on a text interface between transactions and our transformer models. So this allowed us to learn from arbitrary transaction features such as numerical, categorical, string features. Of course, in this case, numerical features relied on this quantization, like we did with the amount. And we saw how experimenting with different transformer models can increase the quality of our at least pre-trained embeddings for downstream tasks. So then we looked at the supervised joint fusion, and we discussed why we needed to be able to incorporate these tabular features into our model. And we showed how we can use joint fusion to take our pre-trained models and learn task-specific features for whatever task of interest we have. Then we saw an application. So we showed how we could take this model pre-training in joint fusion setup and apply it to a particular task of interest, where we got 2.5x the normal improvement that we would try to seek before launching a model online. And we were able to achieve this purely by improving our ability to model the transaction data, not by adding new transaction sources. And then finally, we just talked about what the next generation of these models is going to look like, allowing us to be much more efficient, because we no longer have this situation where a transaction is represented by potentially many tokens. Yeah, that's the end. Thanks for listening.